Hi, I'm Sabin Yaakov. This presentation is entitled More on Transformer Leakage, Turns Ratio, and Voltage and Current Transfer Ratio. There is a very important background video. Here it is, and I'm going to print it on the YouTube page of the video that you are now watching. This video covers the theoretical basis of the material that I'm covering in this presentation. The next few slides might come as a surprise to some of you watching this video, because they are contradicting the basic notions that we have on a transformer, and by that I actually mean an ideal transformer that we seem to have all the time in our mind, but the physical transformer that I'm discussing here is behaving differently. So here I'm showing a basic transformer. Here is the core. There are two windings, N1, N2, and the coupling coefficient is 1. This is one of the requirements of an ideal transformer. Now we know that for a transformer like this, the voltage transfer ratio, V1 to V2, is N1 over N2, N is the number of turns, and the current transfer ratio is N2 over N1. And then we take it for granted that if we have a transfer ratio V out to V2, a given number, then the reverse or backward transfer ratio, that is from V2 to V1, is 1 over V1 over V2. So these are the very basic characteristics of a transformer, but as it turns out, this is correct only for the ideal transformer. When it comes to practical transformer or physical transformer, they do not behave like that. And the main reason is that the coupling coefficient of a practical or physical transformer is never 1. It's impossible to build a transformer with a coupling coefficient of 1 because there is always some leakage, and therefore you can just approach 1, but usually it's lower than 1. And therefore you can just approach 1, but always it will be lower than 1. And this is why for the practical transformer, all these do not hold, as I'm going to show next. In the video that I've referenced, I've shown and proved, in fact, that the very basic model of a transformer is the coupled inductor. In the case of a transformer which is ideal, K is equal to 1. Other transformer, K will be smaller than 1. And then I've shown, which is very important, that once you have this very basic fundamental model, which is coming from textbooks, from physics you might say, then you can transform them to any one of these networks, and in fact to infinite number of networks of different configuration, provided of course that you do the transformation correctly. So here we have a case in which the leakage of the transformer is put on one side and the magnetization inductance also on the same side. Here we have the leakage split between these two, and here we have a all entirely different configuration. All of these have the same terminal characteristic. By this I mean that the input to output transfer ratio of voltage and current forward and backward are the same, and also the impedances are the same. Here I'm going one step further to show the very general notion of coupled magnetic system. Okay, I'm showing here a coupled inductors, and then I've added an external inductor. Now I'm going to define all this as my system, and then I can find, as shown in a previous video, I can find the basic fundamental coupled inductor model of this structure here. Of course, the inductances will be different and the coupling coefficient will be different, but if I do the transformation right, from outside, this looks exactly as this one. And then, of course, if I have this unit, I can transform it to any model, like any one of these, or as I've said, in fact, infinite number of models that you can modify and change and move inductances back and forth, right and left, if you do it right, the terminal characteristic will be exactly the same. So the first fact that I found is difficult to be accepted by some is that if you have a coupled magnetic system, like a transformer or maybe so-called integrated magnetics, and it has some terminals. I'm showing here for the sake of simplicity 2 terminals, but this is a general observation for any system. So if we have a coupled magnetic system, one has to accept the fact that there's no way from outside to tell where are the leakages and what is the inner structure. This is very much similar to, say, Thevenin law. In the case of Thevenin, we know that if we have a system with a number of sources, say DC sources and resistors, we can represent it as one source and one resistor. So this means that from outside, I can never tell if the system is built from one source and one resistor, or maybe 50 sources and 100 resistors that are connected in such a way that can be translated to one source and one resistor. This is exactly this same situation. From outside, it is impossible to tell what is going on inside because there are many options here, and the characteristic of the outside terminals are very general, and this is explained in detail in the previous video. So now I'm moving to the consequence to what we have just said. Just for sake of illustration, I'm assuming now that a practical transformer, a physical transformer, has this model, and I've chosen, for the sake of simplicity, just for the explanation, this particular configuration. I could have used any one of the other configuration, but maybe the explanation would be a little bit more difficult because I had to do some derivation. Here, it becomes very simple. So this now represents a transformer, a physical transformer with some leakage, and in particular, K is smaller than 1. So in this case, if I look at the transfer function between, say, the right side to the left side, I see here a voltage divider. Okay, so obviously we have the voltage being divided, and then it goes through this transformer, which is an ideal transformer in this model. So it is reflected to the output, and the output actually sees a voltage which is related to the voltage drop on L sub B. Now if we consider now the backward voltage transfer, that is assuming that the voltage here, and say this is open circuit here, we see the voltage is imposed on this transformer, reflected to the secondary, and then seen at the output, because I've said there is no load here. So in this case, this voltage divider doesn't do anything. So therefore, in this case, the voltage transformation from here to here is not equal to 1 over the transfer ratio between the left side to the right side. So this relationship does not hold as in the ideal transformer. Now, not only that, in this case, if I change the load and I look at the voltage developed on it as a function of the voltage on the right side, clearly the resistance of the load will affect the voltage, because I actually have a divider from here to the load, and as the load, say, will be higher or the resistance will be lower, I'll see a lower and lower voltage. So this ratio does not hold for any load, and it is load dependent. Not so in the ideal transformer. In the ideal transformer, the voltage ratio is fixed. Same thing goes for the current ratio, which is also load dependent, because if the load is changing, you see that the loading here will change, so the ratio of the current here to the current here will change, and therefore the current transfer ratio will change. So what we see here, just a demonstration, and again I've taken this model just for simplicity. I'm showing here that in the general case, all these do not hold, and that we are going to have a sensitivity to load and different transfer ratio from one side to another and the other way around. And now I'm coming to the third derived fact, which has to do with the relationship between the voltage transfer function and the turns ratio. Now we know that in the ideal transformer, the voltage transfer ratio is equal to the turns ratio. Now, see what happens here. Here is a transformer, and I'm showing here the flux within this winding here. And I'm showing that some of the flux is indeed continuing to the output, if I consider this to be an output. But some of the flux here is sort of lost to leakage of this winding. There is also a leakage of the other winding, which I will not consider now. I'm talking about the leakage of this winding, so there is a portion of the flux which is not coupled to the output. Now, if I impose the voltage on this winding, then I know that the relationship between the flux, or the derivative of the flux and the voltage, is n sub 1 dphi dt, and this is the total flux here due to this excitation. But then the output voltage will be also related to the change in flux, the derivative of the flux, but this flux now is different here from this because some of it got lost. So on the one hand, we have V1 N1 dphi dt of the original flux, and then we have V2 N2 dphi dt of the reduced flux, reduced by the leakage of the primary. I'm just considering the primary here. So therefore, when you divide this by this, obviously you do not get V1 over V2 equal to N1 over N2, because these two are not equal. So the fact is that in the practical transformer, the voltage transfer ratio is not equal to the turns ratio. To demonstrate what I've just explained, I'm going to do some simulation on two units, this one and this one. I'm starting with this. This is a coupled inductor with K equal to 1, so this is like an ideal transformer, plus an inductor. So I'm considering this as a system, a coupled magnetic system. I've extracted the equivalent model, that is the model that behaves exactly like this, as a coupled inductor, a classical coupled inductor with two inductors and a coupling coefficient. Now, these inductors are not the same as this. Obviously, the input inductance here has to be 2 henries now. I'm using here henries just for the demonstration. So the sum here has to be equal to here, because if it's open here and open here, you have to see the same inductance. So obviously this is different from this inductor of the coupled portion here. And also, as one would expect, the coupling coefficient in this case is not 1, and it turns out to be 0.707. So I'm now going to run these two side by side, first of all to show that they do behave exactly the same if indeed I've made this transformation correctly. So here is the circuit. We see here the first network. Here is the inductor, coupled inductor with coupling coefficient 1. Here is the other network, and here we have just a pair of inductors which are coupled by a coupling inductor of 0.707. And in this case, I'm feeding the source or the excitation from the right side, here, and I'm leaving this open circuit, and here open circuit. And then I'm moving the excitation to the left side, here it is, again leaving the other side open, and here it is here. And it turns out, as I'll show in a minute, that in this case the transfer ratio, the voltage transfer ratio is 1, that is between here and here, or here and here, which is the same. And in this case the voltage transfer ratio is 0.5, that is from here to here. Now, if it would have been an ideal transformer, and this would be the transfer ratio here, here it should be 1 over, that is 2. or if this is 1, then this should be also 1. So clearly the simulation supports what I've just said, and here we see the following. This is the case of the backward, and I'm superimposing the input and the two outputs of the two models, and they are practically the same. So this shows, first of all, that the two models are producing exactly the same output, and also that the gain here is 1, because here we have the input and output superimposed. And then this is the forward case. We have the input, and then the two outputs are here, one on the other. This is here 1, and this is the other one. The blue is hiding behind the red, and here the transfer ratio is 1/2, about 1/2, okay, 0.5. So obviously it is not consistent with the concept of ideal transformer. And then I'm doing another run in which I've put a load. Here I have 100 ohms. Here I have 100 ohms. This is for the case of the forward transmission. I call it forward from the left to the right, from the left to the right, and these are the two models. And here it's like backward from the right to the left. I put 100 ohms here as the load, and here's the excitation. Here is the excitation. In this case, as it turns out, for this particular case, of course, the voltage transfer ratio in the two cases is about the same. It is just a private case, of course, and I can assure you that with other resistors it is not. I've just chosen it just to see this particular situation. And here we have it. This is for the forward, this is the excitation, and these are the two outputs superimposed. And this is for the backward, excitation, the two superimposed. And as you can see, the gain is about, the excitation is 1 volt, the output is about 0.2. There is some transient here, so it's about 0.2, and it's about 0.2 here. So this is a really private special case here in which the two are the same. If it would have been an ideal transformer and the transfer ratio is 0.2, the backward should have been 1/0.2, that is 5, which is not. So what are the conclusions here? I'm just repeating the point that I put earlier. The very fundamental fact is that if you have a two-terminal or more coupled magnetic system, there is no way to tell from outside measurement or behavior what is going on inside. There are many ways to describe it, infinite number of ways that you can describe it. All will behave the same from the outside terminal. A derived fact is that the voltage and current transfer ratio are not reciprocal in the general case, because you may have different attenuation on one side and a different one when you go back. And then another derived fact is that the voltage transfer ratio is not the turns ratio in the general case, and that this ratio, the voltage transfer ratio, as well as the current transfer ratio, is load sensitive. You change the load, the transfer ratio might change. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you find it of interest, and perhaps it will be useful to you in the future. Thank you very much.